Let's now see how we can determine the inverse Laplace transform of some more general rational functions. We focus on strictly proper rational functions. A rational function, first of all, is a polynomial divided by another polynomial. We say that a rational function is strictly proper if its denominator has a degree larger than that of its numerator. For example, 2s plus 3 over 5s squared plus 8s plus 1 is a strictly proper rational function. Say that f, which is given by p over q, is a strictly proper rational function. Our approach to determining the inverse Laplace transform is conditioned by the roots of q. The roots of the denominator of the function are called the poles of f. The first case we will examine is when f has distinct real poles. All poles of f are real numbers, different from one another. The trick is to write f as a sum of simpler fractions. This is known as the partial fractions expansion of f. The goal is to write f as the sum of fractions in this form, where in the denominators we have s minus each pole. We have s minus s1, s minus s2, and so on. Then a1, a2, a3, etc. are constant real numbers that we need to determine. The determination of these numbers is now our main objective. It is perhaps best if we explain how to do that, how to do a partial fractions expansion, through an example. Take f of s equal to s over s squared minus 1. This is a strictly proper rational function. It is easy to see that the denominator can be factorized as s minus 1 times s plus 1, and that it has the poles plus 1 and minus 1. We can therefore expand f into partial fractions as follows, with s minus 1 and s plus 1 in the respective denominators. Let us write down the last equation and multiply both sides by s minus 1 times s plus 1 so that we can get rid of the denominators. Next, we observe that we have a polynomial of s equal to another polynomial. We have written the polynomial on the left-hand side as 1s plus 0 to show that the constant term is 0. But two polynomials are equal if and only if their respective coefficients are equal to one another. This yields a linear system of equations. We have 0 equals a1 minus a2 and 1 equals a1 plus a2. We can solve that easily to find that a1 is 0.5 and a2 is again 0.5. We can now plug these values into the partial fractions expansion of f and apply the inverse Laplace transform to get the result. Recall that the inverse Laplace transform of 1 over s minus a is the exponential of a times t. You can try to find the inverse Laplace transform of this function by yourselves. It is evident that the poles of f are minus 1, minus 1/2, and minus 5. They are real and distinct. The objective is to determine real numbers a1, a2, and a3 so as to write f as a sum of partial fractions. You can also try this function. The difference here is that the roots of the denominator are not given. Instead, you need to determine them. You can do that by solving a quadratic equation. Let us do one more example. Here f is a strictly proper rational function with poles 0, minus 2, and minus 1/2. Therefore, we need to determine a partial fractions expansion of this form, the same as we did before. Our objective is to determine the real numbers a1, a2, and a3 of the partial fractions expansion. We write down this equation, but before we proceed, note that on the left-hand side we have the term 2s plus 1, whereas on the right-hand side we have s plus 1/2. A simple thing we can do here is to divide both parts of the left-hand side fraction by 2. Then we proceed as before. We have polynomials on both sides of the equation, and we compare the corresponding coefficients. This leads to a linear system of equations with variables a1, a2 and a3. We solve this system to obtain a1, a2 and a3, and we plug them into the partial fractions expansion of f. It is now easy to determine the inverse Laplace transform of f. Some important qualitative remarks here. Whenever we have a pole at 0, the corresponding inverse Laplace transform is a constant term. For every negative pole, we have a decreasing exponential function, and for every positive pole, we have an increasing exponential. We can conclude that if all poles of f are distinct negative real numbers, the corresponding inverse Laplace transform will be a function of time, a time domain function, that converges to 0, whereas if at least one pole is a single positive real number, then the inverse Laplace transform will diverge.